Welcome guys. So last time we did article 4.2 and I think article 4.2 that was based on the variance and the covariance of the random variable, and I told you variance and is nothing but the sigma square and the square root, positive square of the variance, that is nothing but the standard deviation. So that's what we saw. And the covariance is nothing but whenever you have function of f of xy and g of xy, two dimension. At that time we don't say variance, we say covariance. So that's what we did last time. And today we are going to say article 4.3. This article 4.3 that is based on the means and variance of a linear combination of a random variable. Let me open this one for you and here, means and variance of a linear combination of a random variable. So far we have seen just the random variables and its expected value, means mean in terms of random variables, and then after variance and covariance or standard deviation. But now once you have a function, that means you can always think about the linear combination of that function. Linear combination, I mean to say that suppose you have f1, f2, f3, these are three functions, then you can write c1 f1 plus c2 f2 plus c3 f3. So that is called the linear combination. So all your functions have some weights, c1, c2, c3, or they are multiplied by some constants. You can say c1, c2, c3, and that is called the linear combination, right? So exactly same over here, because random variable is also a function, as we have seen in the last chapter or in chapter number 3. So that is why we can think about the linear combination too. Once we know about the linear combination, naturally one can think about the linearly dependence and independence of the random variables too. That means suppose you can write C1 and random variable, suppose X1 capital X1 capital X2. So C1 capital X1, C2 capital X2 plus C3 capital X3 dot 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 Cn capital of Xn. And if you equate to 0, and if you have all these weights C1, C2, C3 and Cn, all these weights are 0, in that case your random variables, they are linearly independent. And if you have at least one of these constants C1, either C1 or C2 or Cn, if at least one of them is not 0, in that case you can say it is linearly dependent. So once you have a function, always you can think about the linear combination. Linear combination can lead us to the linearly dependent and independent of the vectors or functions or random variables, whatever you can say in terms of the given terminology. So that's what we mean by this one. So now we are going to start the means and variance of a linear combination of random variables. Random variables here we do not write capital X, so we can write this one capital X and like this. So just keep in mind this thing, that all the results that what we are going to present here, they are valid for both cases. One is discrete and another, as you know, that is the continuous case. So discrete case as well as the continuous case. So let me write this one by one. So let me just close this one. So I think I forgot to share the screen. I wanted to share the screen. So let me just share my screen now again. Not this one. My book is over here. Okay. And I want to share my book. My book is over here. Yes. So I think now you can see my screen. So means and variance of a linear combination of a random variable. So that's what we are going to do today. So let me again stop sharing and let me start my whiteboard. So my whiteboard over here, that is, let me first write it down that this is article 4.3. Article 4.3, and it says that means and variance of variances of linear combination of random variables, linear combinations of random variables. And that is true for both the cases, discrete and continuous, for both the cases. My first theorem or definition, you can say, that is in the form of, let me write theorem 4.5 in the book, page number 128. So it says that if A and B are some real constants, in that case, if A and B are some real constants, in that case, we can write expected value of AX plus B, that is equal to A times expected value of X plus expected value of B is B itself. So that is equal to B, because expected value of B, that is always B. Expected value of any number, that is equal to number itself. We know this thing. Right, guys? So please keep this thing in mind, and that is really very easy to prove. Suppose I want to prove the same thing in terms of continuous function. So I can say proof in terms of the second part, continuous function. So that is equal to AX plus B, and that is equal to integration negative infinity to infinity, and AX plus B, exactly same as over here, and my f of X and dx. The same thing can also be visualized as integration negative infinity to infinity x and fx dx plus, because it's a term by term integration, so plus integration negative infinity to infinity, and here it is b is constant and pull it out, and here it is 1 times, or it is f of x and dx, f of x and dx. You can write like this. The first integrand, you can see this is nothing but this is a times, just by definition of e of x, x comes over here, right? And the second integral, that is equal to 1, because we know this thing that integration, that is b, and here it is integration negative infinity to infinity fx, that is equal to 1. So that is equal to this one. So always whenever you have this type of information, this type of expected value, that ax plus b, in that case, you can write that is equal to A out and E of X plus B. We have some corollaries over here. We have some corollaries, and these corollaries are like this, that suppose you have this expected value, whatever I have mentioned over here, it is something like this. See, we know the differential operator too. Suppose I want to say, it's not expected, it is of course mean, but it is something like this. Suppose you have 2x plus 3. So always you can pull this 2 out, and you can write d by dx of x and plus, or if you want to write x squared, then it is x squared, and then d by dx of 3, d by dx of 3. So something like this. So always please keep in mind this thing, that you can pull this one out, but this is different. This is the expected value. Okay, so my corollary, if I take, suppose a is equal to 0, in this case, a equal to 0, then in that case, expected value of ax plus b, that is equal to b itself. And my second corollary, suppose I have b is equal to 0, in that case, expected value of, now a is equal to 0, that means this is 0. So expected value of b, that is equal to b. And that's the reason I just plug this value, that expected value of b, that is equal to b, and b equal to 0 means expected value of ax, that means you can pull a out, and it is expected value of x, I can give you some examples too. Suppose, as for example, suppose my fx is equal to 2x minus 1, some linear function, and suppose I want to find the expected value of f of x, so that is equal to e of 2x plus 1 or minus 1, that is equal to, just by this definition, 2 times expected value of x minus expected value of 1, that is equal to 2 and expected value of x as it is, 2 and expected value of x, right? Expected value of x minus e to the expected value of 1 is simply 1, But I need to find this one. This expected value of x for this function, I can say like this, where expected value of x, that is equal to, you can write nu, because that's the mean, that is equal to summation of x times fx, and x runs from, in my previous example, this fx equal to this one. This is the example of discrete case, discrete, and we are doing the example number 4.4 on page 115. So page 115, 4.4 example is somewhere over here. Let me write it down, this example for you. We are given the data like this. Let me change the color, so probably it will be a little bit easier for you to get this one. So if you have this one and you are given, this is page number 115, example number 4.4. That's what we are referring to. So here it is x, and here it is probability of capital X is equal to small x, and here it is 4, 5, 6, 7, 8, and 9. And we are given the values here that is equal to 1 by 12, 1 by 12, 1 by 4, 1 by 4, 1 by 4, then after 1 by 6 and 1 by 6. And we are using this theorem over here for the same example. The same example is given to you. With respect to this tabular form. Okay, so expected value of nu that is equal to x runs from 4 to 9, you can say. So that is equal to x is equal to 4, and when 4 is there, my fx value is 1 by 12. 1 by 12. So I can write that is equal to 1 by 12 plus 5 and 1 by 12 plus 6 and 1 by 4 plus 7 and 1 by 4 plus 8 and 1 by 6 and plus 9 and 1 by 6. Whatever the value you are getting over here, this value I have calculated that is equal to 41 by 6. Actually 82 by 12, so that is equal to 41 by 6. And whatever the value we have, just go back and plug this value over here. So you are going to get expected value of 2x minus 1 is equal to 2 times it is 41 by 6 minus 1. So here it is 3. So you can write 41 by 3 minus 1. Use your calculator. You're going to get one number. So that is equal to 41 minus. So it is 41 minus 1. That is 3. That is equal to 38. 38 divided by 3, and 38 divided by 3 is 12.6. So expected value is 12.6. So that's how you can figure it out, this thing. So that's what we mean by the expected value. Okay, guys. And then after we have another example. And that example that is for the, I verified this formula. This formula I verified, that is for the discrete case. Same way I can verify the formula for the continuous case. And I would like to go for the next example, 4.5 on the same page 115, page number 115, then same page 115 with the next example, because this is the example for discrete tabular form. Next example was given to us that is in terms of the continuous form. So let me save this part, and then after I will be moving to so in a folder, okay. Save. Okay, so now clear drawing. So now second example that is in the form of the continuous form. Continuous case. So my example is something like this. My fx in the example number 4.5, page number 115. Same example I'm referring, same fx I'm referring over here. So x squared by 3, if x lies between -1 and 2, and otherwise it is 0. Otherwise it is 0. Find the expected value of g of x, and this g of x is given by, where g of x is given by 4x plus 3. 4 of x plus 3. Right, guys? So now let me solve that example. So expected value again of g of x, that is equal to expected value of 4x plus 3, that is equal to 4 out, expected value of x minus expected value of 3, that is equal to 4 out, expected value of x minus 3. And I want to find this expected value, that is the mean. So where my expected value of x is equal to integration, because of x, I can write it down over here, x and my fx, and -infinity to infinity and d of x, that is equal to, but my integration, that is otherwise it is 0, so -1 to 2, and here it is x squared by 3 and this x as it is, and here it is dx. So 1/3 and integration x cube, that is x4 by 4, -1 to 2, and that is equal to 112, and here it is 16 minus 1, so that is equal to 15 by 12. So 15 by 12 can be written as, yes please, 15 by 12, right? So 15 by 12, that is written as, just place 5 3s are 15. So 5 multiplied by 3. And here it is 4 multiplied by 3. So 3 will get cancelled out and we are getting 5 by 4. Just go back and plug this value of 5 by 4 over here at this place. So expected value of 4x plus 3, that is equal to 4 times 5 by 4 minus 3. So this will get cancelled out, and 5 minus 3, that is equal to 2. So that 5 minus 3 or plus 3, it is plus 3, right? My bad. So why I wrote minus, I don't know. It has to be plus. So plus, and here it is plus. So 5 plus 3, that is equal to 8. So that must be the answer. So 8 is the answer. So that's how you can go for the expected value. Now I would like to go for the second one. Second one is again in the form of the theorem. Oops. Where is it? I need to stop sharing, and I need to stop sharing and share this one. Whiteboard. Okay. So now I'm taking theorem number, next theorem, or even write theorem number 4.6, or you can say second rule. That was the previous one. This is the second rule. So suppose expected value of the sum of the differences. So E of gx plus hx, right? Sum or different expected value of the sum of two or more functions of a random variable x is the sum of their expected value, means sum of their expected value or differences of their expected value. So you can consider like this: the expected value of a sum or difference of two or more functions of a random variable x is the sum or difference of the expected value of their functions, and that is given in this form. I would like to take one more example over here as per example, again for the discrete case first, and then after we will be doing for the continuous case. So discrete and continuous. Discrete and continuous case. Okay, so my discrete case example says that suppose I have one tabular form given to us that is equal to x and 0, 1, 2, 3, 0, 1, 2, and 3. And fx is equal to 1 by 3, 1 by 2, 0 and 1 by 6, 0 and 1 by 6. This is my f of x, small x. Okay, and we are given that some function y is equal to x minus 1 square. And we need to find the expected value of this one. So find expected value of y. So I can write the same thing in this form, that expected value of x minus 1 square, that is equal to expected value of x square minus 2x plus 1, that is equal to expected value of x square minus 2 times expected value of x just by the previous theorem, and plus expected value of 1, that is equal to 1 itself. So I need to find, this is my new, I need to find this x square and this one. So first of all, I can find new, that is equal to expected value of x, and that is equal to summation of x and fx dx, or x and fx. So that is equal to 0 times 1/3 plus 1 times 1 by 2 plus 2 times 0 plus 3 times 1 by 6. This 2 times 0 is 0, this is 0. So 1 by 2 plus 1 by 2, and that is equal to 1. So this expected value of nu, that is equal to 1. Now I can find expected value of capital X square, that is equal to summation of x square and fx. So that is equal to x square. I have to take the square of all these things. So it is x square 1 by 3 plus 1 square 1 by 2 plus 2 square and 0 plus 3 square and 1 by 6. So 2, this is 0 and this is 0, no need to write. This is 1 square is just 1, so that is equal to 1 by 2 plus 3 square is 9 by 6. So 9 by 6, that is equal to 3 by 2. So 4 by 2, that is equal to 2, so that is equal to 2. If you plug these values back over here, so you are going to get these values back here, you are going to get that is equal to that is equal to ex square is 2 minus 2 into 1 plus 1. So this 2 and 2 will get cancelled. So that is equal to 1. So that is my answer. That is the answer. Same thing I can do for another example that is for continuous. So let me use, for this continuous case, we are given fx is equal to 2 times x minus 1 if 1 is less than x is less than 2. Otherwise, you can write that is equal to 0. And find the expected value of the function gx is equal to g of x is equal to x square plus x minus 2. So find expected value of g of x. That is the question. So naturally, expected value of g of x, that is equal to x square plus x minus 2 is equal to expected value of x square minus expected value of x and minus 2 as it is. So expected value of 2 is 2. Right, now I can find both of these terms separately. So e of x, that is my new, and that is given by integration x times, here it is this one, this function fx dx, x times fx and dx and negative infinity to infinity. My function is valid only between the region 1 to 2, and here it is x as it is, and here it is 2 is out, and here it is x minus 1, and here it is dx. This is nothing but x square minus x. So 2 times integration is x cubed by 3 minus x square by 2, and that is equal to 1 to 2. So that is equal to 2. And if you open this integral by using the second fundamental theorem of calculus, you are going to get that is equal to, yes please, that is equal to, yes, 1, 2, 3. So, oops. I'm getting some messages. Just wait, guys. Okay, so that is equal to, look at here, that is equal to, here it is 2, and first of all, x is replaced by the upper limit. So it is 8 by 3 minus 1 by 2. In between minus sign, x is replaced by the lower limit. So 1 by 3 minus 1 by 2. And if you open this one, so 8 to the 16 minus 3, that is equal to 13 by 6, something like that. Right, guys? So you will be getting 8 by 3 and x is equal to, so 4 by 2, sorry. So 8 by 3 and 4 by 2 and 1 by 3. So if you open this one, you are going to get that is equal to 2 outside, and here it is 2/3 minus plus and 1/6. And that is equal, if you open this one, you're going to get 10 by 6, and 10 by 6 is nothing but 5 by 3. So 5 by 3, that is my e of x. Now let me just go back. Let me save this file. Let me save this one. And now I don't want to clear the whole part, but I just want to clear the upper part so that we will have some space to write it down. So let me erase the things. Suppose where is my page? Okay, let me just do this thing. Let me stop sharing this one, and I'll be back to my page. Okay, so now let me write it down over here, and let me continue with this, my example. So I am now looking for ex square. So if I write ex square, so e of x square is equal to 2 is out, integration 1 to 2. Here it is x square and x minus 1 and dx. And that is equal to 2. that is equal to 2, and this is nothing but x cube minus x square inside the bracket x to the power 4 by 4 minus x cube by 3 and 1 to 2, that is equal to 2, and 16 by 4 minus 8 by 3 minus, I would say that 1 by 4 minus 1 by 3, and that is equal to 2. 16 by 4, that is equal to 4. So 4 3s are 12 minus 8, that is equal to 4 by 3, minus, I would say that 3 minus 4 is negative 1, so positive 1 by 12. So that is equal to 2, and here it is 4 4s are 16 plus 1 17, 17 by 12. So that is equal to 17 by 6, if I am not wrong, 17 by 6. And then after I'm going to plug all these values over here in this equation. So therefore, expected value of x square plus x minus 2, that is equal to ex square minus ex plus or minus 2, that is equal to 17 by 6 from here, and 5 by 3 from here. So minus 5 by 3 and minus 2, that is equal to 17 minus 10 minus 12 divided by 6. 17, and here it is plus sign, right? So this is plus sign is there. So plus sign and plus sign and plus sign. So that is equal to 27. And so it is 15 by 6, and 15 by 6, that is nothing but 5 3s are 15 and 3 2s are 6. So 5 by 2, that is the answer. So it's very simple. Just one has to pay attention based on the Calc 2 course. Then after, I think we are done with this one. Then after, I would like to switch over to the next one, rule number 3. Let me save this file, and then after again in the next folder, and let me clear the drawing, and I can again go through my third one. Just give me a minute. Rule number 3 is nothing but rule number 3, or if you want to follow the book, it says theorem number 4.7. So theorem 4.7. This theorem says that the expected value of the sum or difference of two or more functions of random variables x and y is the sum or difference of the expected values of those two functions, right? That means I can say that expected value of g of two functions x and y plus h of x and y, g of x and y, and h of x and y, expected value of sum of two functions of two random variables x and y, that is equal to sum of their functions of sum of the expected values, right? That is equal to sum of their expected values of the functions of x and y. So I can write that is equal to E of g of x and y and plus E of h of x and y. Here it is minus, so here it is minus. Here it is minus and minus, right? And I have some corollaries over here too based on this one. So corollary, I would say, suppose 1. So if I take if g of x and y, that is equal to, suppose, simply function of x, and h of x and y, that is simply a function of y, not the function of two variables. In that case, what happened? That E of g of x plus h of y, that is equal to expected value of g of x plus expected value of h of y. Expected value of h of y. And here I have considered as gx and hx, but it could be possible that g instead of gx is just x. So if in more particular way, if I say suppose f of g of xy, that is equal to simply x, and h of x and y, not a function of y but simply y, in that case, then what will happen? That E of g of not g, E of x plus y, that is equal to expected value of x plus expected value of y. Expected value of y. And this is true for negative also, negative also, negative also, and negative also. Right, guys? So that is true for this one. And here I would like to say that our previous, this corollary, this one, the second part of the corollary, it says that the average daily production of both the machines is equal to the sum of the average daily production of each machine. So the average daily production of both the machines, that is equal to sum of the daily production of each of the machines. So if you want to consider this one in a practical form, so you can consider just on a production line machine, two machines are there, then average production of both machines, that is equal to sum of their productions, average productions, right? Then after, I would like to go for suppose fourth rule, and fourth rule that is given in your book, that is equal to theorem 4.8. If x and y are two independent variables, x and y, if x and y are two in random variables, right? X and y are two random variables, but these two random variables, but they are independent. This is very, very important. X and y are two random variables, but independent. Then what will happen then? Expected value of x and y, that is equal to expected value of x times expected value of y. We are not using a kind of product rule over here, but they are separately. You can write expected value of x and y, that is equal to expected value of x and expected value of y. So if they are independent, if they are dependent, in that case, you cannot write like this. This is possible only if your x and y, they are independent of each other. That means suppose you have a card of the deck, and suppose you're looking for one card, suppose jack. So if you take one card out of 52, and suppose you are getting jack, just pick one card. So you are getting jack or not, the different issue. Suppose you are getting jack or not, okay, then replace that card back again, use your card deck and again pick one card, right? Again, one card, whatever you are going to get. So these two trials are independent because it is with the replacement. So there is replacements means independence, non-replacements means dependence. One depends on each other. Second one depends on the first one, like this. So whenever we have replacement means independent trials at that time, random variables x and y, then e of xy equal to ex times xy. That is equal to ex times xy. And as a corollary, you can say, corollary of the theorem, that let x and y be two independent random variables. Corollary, let x and y be two independent random variables, be two, again, independent random variables. Then what will happen? Then sigma xy, that is always 0. Sigma xy, that is always 0. So x and y are two independent random variables, then sigma xy is always 0. Now I would like to go for again one example from the book. One is based on, in the book, based on this theorem number 4.8, right? So let's go for this one, and then after we are going to generalize the probability distribution. So if x and y, okay, that sounds good. So let me go through these two examples first. So let me save this one in a folder. I don't want to clear this one, and let me stop sharing and let me share my book. If I share my book, you are getting okay, we have done up to here. X and y, look at here, x and y are two independent random variables, then sigma xy variance, sigma xy, that is equal to 0. Now look at this example. This is the example for the function of two independent variables x and y. I told you whenever you are given the two independent variables x and y, at that time we rely on page number 97, definition 3.10 of this book. That is the marginal distribution. So whenever you have function of two independent variables, two variables like this, x and y, always think about the page 97, marginal distribution, definition 3.10, marginal distribution. That will help you to separate out your gx and hy, because we want to figure it out from this function, what is my g of x and what is my h of y. That's what we want to figure it out. So, and that can be done only by using the marginal function. So first of all, try to write it down like this. Try to read this one. It is known that the ratio of gallium to arsenide does not affect the functioning of gallium arsenide wafers. Which are the main components of the microchips? Let X denote the ratio of gallium to arsenide and Y denote the functional wafers retrieved during an 1 hour period. X and Y are independent random variables. Please look at this one. X and Y, they are independent random variables with the joint density function, this one. With this joint density function, we are going to figure it out, our gx and hy. So let me write it down. Please keep this thing in mind and read the example too. The example says that so that e of xy equal to ex and ey. We need to double check. We need to double check this definition, e of xy equal to ex ey, for this particular example. Let me write down this one on my whiteboard. X by 4 and 1 plus 3y square. X lies between 0 to 2, y lies between 0 and 1, otherwise 0. So let me stop sharing this one and let me start sharing my whiteboard again. So I think it's better if I clear the drawing. Let me clear this drawing and let me write it down separately. Okay, so example number 4.21 in the book. So example 4.21 in the book, we are given f of x and y that is equal to x and 1 plus 3y square divided by 4. This is x. If 0 is less than x is less than 2 and 0 is less than y is less than 1, otherwise it is 0. Okay, now my g of xy from the definition of the marginal distribution. So from page 97, definition, what is the definition? I think 3.10. Marginal distribution. Marginal distribution. So in that distribution, we are given g of x is equal to integration over y, and here it is f of xy and dy. F of xy and dy, and h of y is given over the integral of x, and here it is f of x and y and d of x. So integrating just with respect to x. Okay, so that is equal to, here y runs from 0 to 1, f of xy equal to x by 4 and 1 plus 3y square and dy. Here x runs from 0 to 2 and f of xy is x by 4 and 1 plus 3y square and d of x. So here you are integrating just with respect to y. So let me write that is equal to 1 plus 3y square out divided by 4. And here it is integration of x and, my bad, other way around. Where is it? Eraser. So let me erase this part. Okay, sorry guys. And that is equal to integration with respect to y means I can pull it out, my x out of integral sign. So y is equal to 0 to 1 and 1 plus 3y square and dy. That is equal to x by 4, and here it is y plus 3y cube divided by 3 and 0 to 1. That is equal to x by 4, and here it is 1 plus y cube, 1 plus 1, otherwise it is 0. That is equal to 2 and 2, so that is equal to x by 2. So that is equal to x by 2. So I am getting my g of x that is equal to x by 2. g of x is equal to x by 2. Here I'm going to get that is equal to, with respect to x, so 1 plus 3y square is constant. You can pull it out, and under the sign of integral, you have x is equal to 0 to 2 and x and dx. Then that is equal to 1 plus 3y square divided by 4, and here it is x square by 2 and 0 to 2. 2 square is 4 divided by 2 is 2. So here it is 2 and here it is 2. So you're going to get 1 plus 3y square divided by 2. 1 plus 3y square and divided by 2. So now I'm going to write, so this is my first part, this is my second part, and now I'm going to write e of x and y. So e of x and y, that is nothing but the integration along x and then along y. X is equal to 0 to 2, y is equal to 0 to 1, and f of xy, because xy, so I have to write x and y over here, x and y over here, and f of x and y and dx and dy by definition. So that is equal to y is equal to 0 to 1, x is equal to 0 to 2, xy is here, f of xy, that is x, so it is x square and 1 plus 3y square and divided by 4. So xy, and here it is dx and dy. So I can take this integration first and other one is second. So y is equal to 0 to 1, y is equal to 0 to 1, and with respect to x, means all y I can pull it out. So y and 1 plus 3y square divided by 4, and here it is x square, so x cubed by 3 and 0 to 2 and dy. So that is equal to 4 3s are 12. So let me pull it out, 1 by 12, and here we are going to get 2 cube is 8. So let me write this 8 out, to 2 cube. Yes, so 2 cube is equal to 8 if I'm not wrong. So let me pull it out, and here you are going to get y is multiplied over here, so that is equal to y, so integration is y square by 2 minus 3 and y cube, so y to the power 4 divided by 4, and range is 0 to 1. I am right now opening my double integration, right guys? So this can be written as, that is equal to, yes please, so that is equal to 8 by 12. So 8 by 12, that is 4 by 6. 4 by 6 means 2 by 3. So I can write 2 by 3 over here. And integration over here, y square by 2 and 3y square by 4, right? Plus sign is there. I don't know why I'm writing minus. So that is equal to y square is 1 by 2 plus 3 by 4. Otherwise it is 0. So that is equal to 2/3 and 1 by 2 and 3 by 4. So 1 divided and multiplied by 2 here. So 2 plus 3, that is equal to 5 by 4. So that is equal to 5 by 4. So here it is 2. So I'm going to get 5 by 6. 3 2s are 6. So 5 by 6. This is my left hand side actually, because I'm verifying exy equal to ex and ey. So now I'm going to take my right hand side. My right hand side is nothing but e of x and e of y I need to find separately. So my e of x is nothing but, help me guys, e of x, that is equal to, x is equal to 0 to 2 and x is there. So x and f of xy, no sorry, x and g of x, right? G of x dx, that's what the definition says. And e of y, that is equal to, y is equal to 1 to 2, 1 to 2 or 0 to 1? Y is equal to 0 to 1, sorry. Y is equal to 0 to 1, and here it is y and h of y and dy. That's the reason I figure it out, my x and y separately. Gx is nothing but x by 2. So here I'm going to get 1 by 2 and this is x by 2. This x and x is x squared. So integration is x cubed by 3 and here it is 0 to 2. So that is equal to 2 cube is 8 by 3. So 8 by 6, that is equal to 4 by 3. 8 by 6, that is equal to 4 by 3. Same way, suppose I write that is equal to hy. Hy is equal to 1 plus 3y square by 2. So 1 by 2 is out and y is equal to 0 to 1. And here it is y and 1 plus 3y square and dy. This is nothing but y plus 3y cube. If you take the integration like this, so that is equal to 1 by 2 and integration is y square by 2 plus 3y to the power 4 by 4, and integration is 0 to 1. Integration is 0 to 1. If you use the second fundamental theorem of calculus, you're going to get that is equal to 5 by 8. Just replace this y by 1 and then 0 in between negative sign. If you take the product of this one, so ex times ey, because that is actually my right hand side, ex times ey, ex times ey. So ex is nothing but 4 by 3 and ey is nothing but 5 by 8. So here it is 2, so that is equal to 5 by 10. 5 by 6. This is equal to 5 by 6. And you can see over here, this is my left hand side and this is my right hand side. They are same. That means this formula is verified. So that means E of xy, that is equal to E of x times E of y. E of x times E of y. So whatever theorem I explained to you, that is verified. So that is okay over here. Okay, guys. So if you want, I can keep this one here for a minute, and then after I can continue with the next formula. Next formula is the formula number 5. Formula number 5 says that, because once we are almost at the end of this article, and then after we are solving some of the examples from your exercise, and that's it. And we are done for today. So let me save this one, and then after. Okay, so let's clear this drawing and let's start with the next one. Okay, so next part is nothing but theorem number 4.9, theorem 4.9, or I would say formula number 5. Now, whatever we did just previously, that was based on the independent variables. But what will happen if our variables are dependent? If x and y in theorem 4.8, I told you that x and y, they are independent variables, random variables, then expected value of xy, x product y is equal to expected value of x times expected value of y. Same thing over here, guys. Suppose, not same actually. Suppose x and y are dependent variables. If x and y are dependent variables with the joint probability distribution, with the, now joint means f of xy, joint probability distribution function f of x and y. Joint means x and y too, x and y. And a, b, c are constants, and a, b, and c are real numbers, or you can say constant. In that case, what happened then sigma square ax plus by plus c equal to, look at here, guys, here it is a square of sigma square of x plus b square of sigma square of y plus 2ab sigma of xy. 2ab sigma of xy. Not exactly, but in the rough sense, you can say something like this, because now with this dependent. Now in the book, this word is not used, but please keep this thing in mind that x and y are variables. It's just mentioned like this, but actually it's a dependent, not where random variables, dependent random variables. X and y are dependent random variables. In that case, you can say that a plus b whole square equal to a square plus b square plus 2ab, something like this type of formula, a square plus b square plus 2ab. Look at here, a square plus b square plus 2ab. But suppose a and b are distinct, a and b are independent. In that case, a plus b whole square equal to a square plus b square. This is for independent case and this is for dependent case. So not exactly, but something like this we are doing over here. So sigma square of ax plus by plus c is equal to this one. And we have some corollaries over here too. corollary, suppose 1. So if I take suppose b equal to 0, when b is equal to 0, then sigma square plus ax plus c, that is equal to a square and sigma square of x plus sigma square of x, right? And sigma, this is, we don't write sigma of c because that's always 0. Look at over here, there is no related to c, nothing related to c. That is equal to 0 actually. Sigma of c is equal to 0. So that is equal to, sometimes people write this one as sigma square x, a square sigma square. It is to be understood that a is there, means here it is you are working with x. It is just to be understood. Suppose second corollary is, suppose I have a is equal to 1 and b is equal to 0. If a is equal to 1 and b is equal to 0, in that case, what will happen? That sigma square a equal to 1 now. That means I have simply x. B equal to 0, no need to write, so plus c. So that would be written as, now it is, nothing is meant say equal to 1, means here you can write 1 square and sigma square x. Right? And for sigma c, we don't write anything, but 1 square is simply 1. So you can write sigma square x, or in short, you can write just sigma square. And my third corollary is something like this. Suppose I have b is equal to 0 and c is equal to 0. In that case, I can write sigma square a, b equal to 0, c equal to 0. So sigma square of ax. Sigma square of a is a square sigma square of x, and that is equal to a square of sigma square. You can write shortly in this form. Right, guys, so this is for this one, and I would like to extend the same idea for the independent variables too. So suppose I have another corollary. So I would say this is corollary 1, and now corollary 2. Corollary 2. If x and y are independent random variables, if x and y are independent random variables, if x and y are independent random variables, then what will happen? Then sigma square ax plus by independent random variable. Guys, that means this two part is not, this will not be there now. This part will not be there. That means you are going to get a square sigma square x plus b square sigma square of y. That's it. A square sigma square of x plus b square sigma square of y. And suppose somebody says that, suppose corollary, this is one second part, x and y are independent random variables, right? Suppose I replace this b by negative b. If b is replaced by negative b in the first case, in one, then what will happen? A square and ax minus by is equal to a square sigma square x plus b is replaced by negative b. So b square sigma square of y. That means I'm going to get a square sigma square of x plus b square sigma square y. That means if whether it is a plus ax plus by or ax minus by, both the cases we are getting the same one. We are getting the same values. So a square sigma square x plus b square sigma square y. And we can extend the same idea in a generalization. We can extend the same idea for n number of random variables independent. So x1, x2, dot, dot, dot up to xn, n number of independent random variables, n independent random variables. Then what will happen? Then sigma square of, I would say that a1 x1 plus sigma square, oh my bad, a1 x1 okay, then sigma square of a1 x1 plus a2 x2 plus dot 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 an xn can be written as is a1 square sigma square of x1 square plus a2 square sigma square of x2 square, right, plus a3 square sigma square of x3 square dot 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 plus an square sigma square of xn square, sigma square of xn square, right? So that is the generalization. That is the generalization. We have one example over here actually that is not okay. Let me go through that example too. So that example says that suppose you are given example. Suppose you are given the random variable sigma x square is equal to 2 and sigma y square is equal to 4. And the covariance means two variables, sigma xy that is equal to -2. Find the variance of the random variable z is equal to, find the variance, or sorry, sigma variance of the random variable, or sigma square, you can say, that is equal to 3x minus 4y plus 8. So 3x minus 4y plus 8. Find this one, variance of this one. And that is given over here, z. So that is equal to sigma square 3x minus 4y plus 8. So this is your a. So I can write sigma 3 square of sigma square x minus 4 square of sigma square y. Right? 4 square of sigma square y. And they are random variables. Okay, so they are dependent. They are dependent, right? So if they are dependent, x and y dependent. If they are dependent, then you have to go for 2ab. So minus 2a and b. So 4 3s are 12 and 2 24, right? 24. So minus 24 minus 24 2ab sigma xy. So sigma x and y, 24 sigma x and y. You are given the values. Here it is 9, here it is 2, minus 4. And because here it is minus, even though we are writing plus, so we have to make sure that it has to be plus, right? Because for minus also be equal to minus, we have a plus sign here. So plus, okay, so plus 16 and sigma square is equal to 4 minus 24 sigma square xy equal to -2. If you take this product, whatever the number you're going to get, 130, that is the answer. That is the answer. So x and y denote the amount of two different type of impurities. Now I'm going to take another example. This is the example based on x and y. X and y both are dependent. Same way you can take the x and y, suppose they are independent. If you take x and y independent, let me just save this page. Okay. And if you go for, let me clear this page too. So my next example, 4.23. So example 4.23, it says that if x and y are the amounts of two different types of impurities. Now different types of, we are talking about the impurities, but they are different types of impurities. This different type of impurities implies that they are, he's talking about the independent variables. Independent variables, right? Different type of impurities in a batch of the certain chemical product. Suppose that x and y are the independent random variables. It is mentioned here clearly, x and y are independent random variables. Right? It was not the case in the previous term. Independent random variables. Okay. And we are given simultaneously that sigma square x is equal to 2, sigma square y is equal to 3. Find the variance of the random variable. Z is equal to 3x minus 2y plus 5. Find sigma square of z. So you can see over here sigma square of z, that is equal to sigma square of 3x minus 2y plus 5, that is equal to 3 square, sigma square of x plus -2 square, and sigma square of y plus, no need to write anything because it is independent variable. So that's it. So that is equal to 9, and sigma square is 2 plus 4 and 3, that is equal to 18 plus 12, so that is equal to 30. So that is equal to 30. So that's how you can solve the examples based on these terminologies. And now we are going to take some examples from the exercise problems, and then we will stop. So let me go over let me go over some examples over here. So my example starts with, we are not going to do anything more from this chapter. Some probability distribution is there. The probability, let me just show it to you. Let me save this page. Okay, and let me stop sharing and let me share my book. If you go for this one, you are going to get this. That's what we have done. And there is nothing but one more thing that is called the Chebyshev polynomial. Chebyshev's polynomial, Chebyshev's function or theorem that is given something like this. Just try to read this one, the variability of a continuous observation about the mean and discrete observation about the mean. These two things are given. In that case, the probability is always greater than or equal to 1 minus 1 over k square. So Chebyshev theorem says that probability that any random variable x will assume a value within k standard deviations of the Look at over here of the mean is at least within k standard deviations of the mean from left and right. That is at least 1 over 1 minus 1 over k square. And that is given in this form, but that's fine. Let me start with these some examples. Just yeah, so here suppose you have k equal to 2 or like this, so 1 minus 2 square or k equal to root 2. So 1 minus 1 by 2, that is equal to 1 by 2. So probability lies between negative 1 by 2 to positive 1 by 2, something like this. So that's what it means. Suppose k equal to 2, 1 minus 1 by square, that is equal to 3/4. That is equal to 3/4, and that is my k value. So nu plus or minus 2 sigma, right? So nu minus k sigma and nu plus your probability value x that lies between nu minus k sigma. So first of all, you can find nu plus or minus 2 sigma because k is equal to 2. So nu plus or minus k sigma, k equal to 2, so 2 sigma. You are going to find nu. Nu is your mean, standard deviation, and then out of plug the values over here, you're going to get two real numbers. So your probability value will lie between these two numbers. That's what Chebyshev polynomial says. Okay, that's fine. Let's go for example number, which one? I think all are good, but let's go for 4.55. Example 4.55 says that we are going to do 4 more examples and we are done. Suppose that a grocery store purchases 5 cartons of slim milk at the wholesale price of 1.20 per carton and retails the milk at the rate of 1.65. 5 cartons they are selling that on the wholesale, slim milk, and they are getting this 5 cartons at the rate of 1.20 per carton, and they are selling that milk at 1.65 per carton after the expiration date. Now it may be possible that till the expiration date, some of the cartons are left out, they are not being sold. So after the expiration date, the unsold milk is removed from the shelf and the grocerer receive a credit from the distributor equal to 3/4 of the wholesale price. Now, what was the wholesale price? Wholesale price you can see over here, that is equal to 120. And that grocer, he is getting the credit of 90%. 3/4 means 75%, right? Okay, so 120 you can divide 3/4 of 120, that is equal to 3/4 of 120 is 90. So 90 cents he is going to get. That grocer is getting back the discount price equal to 3/4 of the wholesale price. If the probability distribution of the random variable x, the number of cartons are sold from this lot is now 1, 2, 3, 4, 5. 5 cartons are there, right? And you are given the probabilities like this, but it could be 0, 2. So actually it is how many? 1, 2, 3, 4, 5, and 6. So don't forget that we have 6 rows. Okay, and find the expected profit. find the expected profit. Whenever you are working with this type of practical example, always keep in mind this thing that you have to be very particular about mentioning your random variables x and y. So I would say that suppose I have 4-point exercise 4.55, and it says that suppose I have let x be the number of cartoons sold. So let x be the number of cartoons sold and let y be the profit. Let y be the profit. So my y will be a function of 1.65 of x, right? Because that's the number of cartoon he is getting on the, he's selling on this price. Then how many cartoons are sold? X number of cartoons are sold. And suppose you have 5 minus x, because there are 5 cartoons, 5 minus x number of cartoons are sold, and 3/4 of credit means 90-cent credit he is getting for the unsold cartoon. And how many are sold? How many rows are there? 6 rows are there, right? Because we are given over here. Let me write this one for you just for your convenience. So here it is x and here it is f of x, and here it is 0, 1, 2, 3, 4, and 5, 3, 4, and 5. So that means I can get here it is 1/15th, and here it is 2/15th. Here again it is 2/15th, then 3/15th, then 4/15th, and again 3/15th. So 1, 2, 2, 3, 4, 3. 1, 2, 2, 3, 4, 3. Okay, so this is my function, guys. If you open this one, you are going to get that is equal to 1.65x and here 90x, right? 0.90x. So 1.65 and 0.90. This is 5. So 9 5s are 45. So 4.50. So I would say that is equal to 0.75x plus 4.50 minus 6, and that is equal to 0.75x minus 1.50. This is my y, or you can say y of x, that is equal to this one. So now I can write my expected value of the linear combination is 0 times 1 over 1/5, right? So my expected value, my function is done now. 0 times 1/15th plus 1 times 2/15th plus 3 times 3/15th plus 4 times 4/15th plus 5 times 3/15th. 5 times 3/15th, right? And you are going to get one number over here. Whatever the number, if you use your calculator, you're going to get that is equal to 46 divided by 15. Once you have this number, then after you can write, this is E of x, and then E of y, that is equal to, once you have E of y, that is equal to 0.75 E of x, and that's what we require here. So we can plug the value from here, and plus this is just constant, 0.75, this is just constant, so no need to write. That is equal to 0.75 times 46 divided by 15. And whatever the number you are getting, that is the answer. So you're going to get over here $0.80. So the total profit is 0.80 cents per cartoon. So that's how you can solve the example. Example number 5.57 is exactly similar. This is a discrete case, exactly similar discrete case for 5.57 also. Let me solve 5.57 if you want, and then we can switch over to 5.58 in our book for the continuous random variable and linear combination. 5.57 says that okay, and then let me clear the drawing. Then I can go for example number 5.58. 57. I can take this example for you. Let X be a random variable with the following probability distribution, and that probability distribution is given by 4.57. That is given by X, and here it is 3 or -3, 6, and 9. -3, 6, and 9. And f of X, that is equal to 1/6, 1/2, and 1/3. 1/2 and 1/3. And it says that find the expected value of X, expected value of X square. Then using the random variables evaluate E of 2x plus 1 square. E of 2x plus 1 square. So we need to find these three items. Okay. So solution says something like this. Suppose I have E of X. So E of X, that is equal to, that is very simple, right? Just multiply this with this. So it is -3 multiplied by 1/6, 6 multiplied by 1 to 9 multiplied by 1/3. And you are getting one number, 11 by 2 and 3 and so 1 by 3. And here it is 3. So 3. So 11 by 3, not 2. Right? And then after I can find E of X square. X square means I need to take -3 square and 1/6 plus 6 square and 1/2 plus 9 square and 1/3. Right? So that is equal to, if you open this one, 3 square is 9. So here is 3/2, and here it is 6 square is 36 and 2. 1/18, and this one, so 2 and 61, 63 and 30, 93. So it is 93 divided by, you please use your calculator, okay? So 93 divided by 2, and find same way I can find the 2x plus 1 square. So that is equal to expected value of 4x square plus 4x plus 4. 4x square plus 4x plus, my bad, that is plus 1. So that is equal to 4 and expected value of x square plus 4 and expected value of x and plus expected value of 1. 4 into expected value of x square, already I figured it out, that is equal to 93/2 plus 4 and expected value of x is 11/2 and expected value of 1, that is equal to 1. And that is equal to 93, 4, 3 are 12. So 1, so it is 2 and 1, 9, 36 and 37 by 2, and plus here it is 44/2 and plus 1. So that is equal to 44. So 372 plus 44 plus 2 divided by 2. And that is equal to 2 and 4, 1, 8 divided by 2. So it is 209 if I'm not wrong. So it is 209. So that's how you can solve the example based on this is also a discrete case. I would like to take one more example, 4.58. 4.58. Simple example. It says that you are given one function fx is equal to, here it is x and 0 is less than x is less than 1. Here is 1 is less than or equal to x is less than 2. Your value is 2 minus x, and otherwise your value is 0. So this is your another example. So I can write this one as, and it says that y is equal to, you are given y is equal to 60x square plus 39x. Here y is equal to the number of kilowatt hours expected annually. Okay, the total time measured in units of 100 hours that a teenager runs her hairdryer over a period of 1 year is a continuous random variable x that is defined like this, that has the density function like this. Use theorem 4.6 to evaluate the mean of the random variable y equal to this one. Y is equal to this one, where y is equal to the number of kilowatt hours expanded annually. Okay, so first of all, let me find E of y that is equal to, so first of all, E of y is equal to expected value of 60x squared plus 39x. That is equal to 60 and expected value of x squared plus 39 and expected value of x. Here I can write expected value of x is given by, that is equal to integration 0 to 1 and x and these x and this function value x, so it is x square and dx. So x cubed by 3 and 0 to 1, so it is 1/3. And then after e of x square, that is equal to, here it is x square and oh my bad, this is 0 to 1. I forgot the second part. Let me do it again. Eraser. That sounds good. And so plus I say that 1 to 2 and here it is x and 2 minus x and dx. Otherwise it is 0. That sounds good. So that is equal to 1/3 is the answer for the first one. Here is nothing but 2x. So it is 2x squared by 2 minus x squared. So x cubed by 3. Right, and range is 1 to 2, and that is equal to 1/3 plus 2 cube is 8 minus 2 cube is 8 by 3 minus 1 minus 1 by 3, right? 1 minus 1 by 3. So expected value of x you are going to get this way, that is equal to 8 by 3, 8 is out, and 1 minus 1 by 3, 2 by 3, and 2 by 3, this is 1 by 3 and 1 by, that is equal to 1, so that is equal to 1. Right, and ex square, that is equal to x square, and in between 0 to 1 it is x square times x, so it is x cubed dx, plus between 1 to 2 it is x square and 2 minus x and dx. Same way you can solve this one and you're going to get x to the power 4 by 4 and 0 to 1 plus this is nothing but 2x square minus x cube. Integration is 2x cubed by 3 minus x to the power 4 divided by 4 and the range is 1 to 2. If you plug the value here, you're going to get 1 and here you're going to get 2, 3, 18, 8, so 16 by 3 minus 16 by 4 minus 2 by 3 minus 1 by 4. So if you calculate this one, you are going to get that is equal to 2 and 3 and 6 and 3, 4 and 6. 6 plus 1, that is equal to 7 by 6. 7 by 6. So just go back and plug these values here. Ex square equal to 7 by 6 plus 39 and ex is equal to 1. Whatever you are getting, that is your answer. So this way you can go for the continuous random variable too. And now let me go for one of the examples based on the variance 4.62. So let me save this file and let me clear the drawing. And we are going to go for the next example, that is equal to 4.62. So 4.62 says that if x and y are independent random variables with the variance sigma square of x equal to 5, sigma square of y is equal to 3, find the random variable expected value or find the variance of the random variable. So variance of z, that is equal to find the variance of z and z is given by what? Negative 2x plus 4y minus 3. Negative 2x plus 4y minus 3. Okay, so this can be written as, guys, look at over here, sigma square of negative 2x plus 4y minus 3 is equal to negative 2 square and sigma square of x plus 4 square and sigma square of y and sigma square of y, right? Is there anything else mentioned over here? Total time measured in units of 100 hours, that's the teenagers runs the hair dryer at the period of 1 year. No, I'm sorry, my bad. X and y independent random variables. Guys, independent, x and y are independent. It's mentioned. It's independent. That means you don't have to go further. This is 0, right? Nothing is else. Nothing else is over there. So 4 and sigma square is 5 and 16, and that is equal to 3. So here it is 20 and 48. And here it is 68. So that is equal to, you can say 68 hours. right? 68 hours. And I would like to go for example number 4.33, in which X and Y are dependent. So I think I took almost all type of examples. Repeat the exercise X and Y, the same example with sigma xy equal to 1 for X and Y are not independent, means dependent. So sigma square of negative 2x plus 4y minus 3 is equal to 4y minus negative 2 square sigma square x plus 4 square sigma square y plus 2a is negative 2 and b is 4 and sigma square of xy. So that is equal to 4 sigma square is 5 and here it is 6 and sigma square is y is 3 minus 16 and sigma square xy is nothing but, yes please, sigma square xy, that is equal to 1. So that is equal to 68 minus 16, that is equal to 52, right? So that is equal to 52 hours. Okay, so that's how you can solve the examples. I think I took the enough examples based on this exercise, and rest of the things you can do later. So that's almost the end of this chapter. And next time we are going to start the some continuous probability distribution. Let me just save this one also. So save this file, this one, and now I can stop over here. This is the end of the chapter, guys. And next time we are going to start the new one, that is some discrete probability distribution. Some discrete probability distribution. So I can now show you the examples over here in the book. If somebody is interested, look at the examples in the book. This is the examples we have taken. We took this example, we took this example, then after we took this example 6.62, 63. All these things are done. So they are just quite simple. Just try to go through it. I don't think that you're going to face any problem solving these examples, and that's just the end of the chapter. And next time, let me just give the flavor that next time we are going to start the new chapter, and that new chapter is some discrete probability distribution. Chapter 5 is discrete probability distribution. Chapter 6 is continuous probability distribution. That is chapter 5 and chapter 6. Anyway, but let me stop over here. We will continue with this one next time.
Okay.
Thank you, guys. Thanks for your patience, and let me stop the recordings to